This antenna amplifier has 3 stages. It has a first amplification stage with a JFET. You have an impedance matching and converting stage with a 2N3904 bipolar junction transistor. And you have an amplification stage with an 8603 from Analog Devices, another amplification stage with a variable gain. The antenna signal is decoupled with 100 nanofarad and directly connected to the gate of this JFET. This output of the JFET is decoupled with, again, 100 nanofarad into the base of the 2N3904. And then this output is decoupled another time with 100 nanofarad to the input of the 8603. JFETs are very interesting components and are often used at the VHF, UHF, HF amplification stages because they have almost no input current. The gate is reversed biased. This is a reversed biased PN junction. And so the maximum current, gate current, of a reversed biased PN junction is something between 1 nanoamps and 1 microamp. It's pretty temperature dependent. You see that's a factor of 1,000 over this temperature range. That's, I think, 25 degrees and 125. But anyway, even 1 microamp is very, very low current. And so the input is not loaded by the gate. The JFET itself, this J310 that I'm using here, is a rather old component. The TO92 housing of this component is obsolete, at least at DigiKey. You can find some J310s in a TO92 still on eBay or AliExpress, but what you still can find are SOT23 surface mount packages, and that's what I'm using here too. Interestingly, this is a depletion mode FET. Depletion mode FETs have a conducting channel at gate voltage 0. So this N-channel depletion mode means at no gate voltage you have the maximum current from drain to source, you have the lowest possible resistance. So this channel is wide open in the sense that it is not pinched off in any form in any way. The more you reduce the voltage at the gate, you make the gate more negative compared to the source, minus 1 volt, minus 2 volt, minus 3 volts. The more you do this, the narrower the conducting channel becomes, and eventually the channel will be pinched off absolutely, completely. So there is a cut-off voltage at which no current flows anymore from drain to source. The JFET is cut off. Typically, this is around minus 3.5 volts. At VGS 0, at the point where gate voltage is 0, you have the maximum current. And the maximum current for these JFETs 310 this current is between 24 and 60 milliamps. We are going to measure this current, this IDSS, on the bench, but be aware, if you apply 12 volts, for instance, 12 volts between drain and source, and you apply no gate voltage for a short amount of time, you can do this test and measure quickly the IDSS, but the maximum power is exceeded. I think the maximum power of J310 is roughly 250 milliwatt, depending on the package, maybe even. And of course, with 12 volt and 30 milliamps, you're above it. So you can only do this for a very, very short amount of time. Otherwise, you blow it up. So JFETs, field effect transistors, have the characteristics of controlling the current flow by the electric field provided through the gate. So there's no current flowing into the gate. This is different with a BJT, with a bipolar junction transistor, whereas the gate current, the base current, is controlling the collector-emitter current. It's a current amplification. You have a small base current and a large collector-emitter current, and you have this amplification factor beta in between. And this is different here. Only the field, the electric field, is controlling the flow of the current. And what is also very nice is that these JFETs typically have a lower noise and lower current noise than BJTs. So you should be able to reduce the noise level with amplifiers like this. Well, now let's take a quick look at the bench, if we can characterize this J310. Well, hello, we are here on the bench looking at the JFET 310 installed here, an SMD component, and you see the gate, the drain and the source. The drain is hooked up to a power supply. The source is hooked up to ground. I have to connect this manually to turn it on and off. And the gate voltage is actually taken from a simple 9-volt battery. And the polarity is such that the gain voltage goes from 0 to minus 3-4 volts. And I use this trim pot to adjust the gate source voltage. And here, let me see if I can show you this. Alright. So now what we see here on the left side, the gain source voltage. The gate source voltage can be adjusted by this potentiometer, and I can increase it to minus 1 volt, 2 volt, 3 volts and so on. At the moment it's at 0 volt. The power supply voltage is at 12 volts at the moment. That's the power supply voltage of my transceiver. And here we measure ID. And since we have no biasing transistors or any current limiting components, we really just have the 310 hooked up directly to the power supply. If you connect source to ground, immediately the maximum possible current is going to flow, and this current is around 30 milliamps times 12 volts, and then you exceed this 250 milliwatt maximum power. So you can do this only for a very, very short time. I just quickly turn on and immediately have to turn off again, and we measure the ID, the maximum ID current, which is specified, I thought, from the specification somewhere between 24 to 60 milliamps. So let's see where this current goes. I quickly connect, and it goes at around 30-31 milliamps. Immediately it starts dropping because it heats up so quickly. So at 12 volt, that's the point, 12 volt ID VGS, the gate voltage 0, and then we get about 30 milliamps. So let's see where we get if we increase the gate source voltage to minus 1. That's around here, -1 volt at gate source. We do this again, quickly connect, and we are down to 18 milliamps. And that's how you take all these measurements going through the characteristics. We are now at -2 volt, and -2 volt gives us roughly, hold on, -2 volts, we are down to 6 milliamps, 6.6. So, and if we go further down, so now we are in the safe mode. If we go further down to -3 volts, we still have 0.4 milliamps. And now it's all pinched off, no current anymore at -3.4 volts roughly. So let's change the voltage from 12 volt maybe to a more safe area of, let's say, maybe 5 volts or so. So we are 5 volts, and then we can go up again to, let's say, -1 volt gate source, and we have now 18 milliamps at 5 volt at the drain source voltage. And now what's interesting, if we vary the voltage now, the current, these 18 milliamps, stay more or less the same. So we go up with the voltage, 11, 12 volts, and then down again, and you see it stays almost the same, 18 milliamps. Now, of course, at 1 volt it starts to drop here. 16, 17, 18. Now we are at 18 at around 4 volts. So between 4 volts and 12 volts, we more or less have 17, 18 milliamps. So it's a constant current, and that's one of the characteristics that you have with these JFET transistors, or FETs as well. Alright, I guess that was it. And let's take a look at the measurement results then. So these are the values we just measured on the bench. We measured between 12 volts and almost 0 volt at drain source voltage, and we measured the current in milliamp in respect to the gate source voltage. So you see here the output current. We had at VGS 0, we measured roughly about 32, 31, 32 milliamps. We have a cutoff region here of about 2.63 volts. You always want to stay above here, above this 2.6 volts in the linear region. This is so-called the ohmic region, where you have, this is a characteristic of a resistor. But we want to stay in here. We want to have our output swing and output modulation in this range, and be sure that we're not getting into the nonlinear range, so that would just increase additional errors. So we have this typical characteristics of exactly our component, and now we can go ahead and calculate the bias points. For doing this, we choose this so-called self-biasing principle. And this is very easy with JFETs. That makes it so convenient, because there is no input current into the gate. We can just take a rather large resistor, 100K, 1 meg, maybe even 10 meg, 5 meg, and pull the gate to ground. So by doing this, the gate is grounded. And that means you can play now with the source voltage. If you apply defined current here and increase or decrease the current through this resistor, you will this gate will become more negative compared to this voltage. So you will have a negative gate source voltage. That's how it works. We choose, so I did choose here a 10 milliamp current. This is my chosen working point. I want to have 10 milliamp here. You saw before these IDSS are typically between 24 and 60 milliamps, so I would choose 10 milliamps, figure out. And since power consumption is not really an issue for my transceiver, then that seems to be fine. So with 10 milliamps, an IGSS of about, I took here 30 milliamps, we measured 32 actually, let's say 30 milliamps. At the VGS off of minus 3.8 volt, that's this point here, where it's really cut off, there's no current flow anymore from drain to source. Then we can calculate with this formula a voltage at gate source of minus 1.7 volts. So we should have this point here should be at 1.7 volts. Since this is 0, we have a minus 1.7 volt at the gate in respect to this voltage, to this point, to this source, to the source of the JFET. So 1.7, 10 milliamps, 170 ohm. I did play around with 120 before, but I changed it to 170. And then maybe we want to have an output swing of plus minus 1 volt, and we mentioned before we shouldn't get into these clamp voltage of 2.6. We shouldn't get below 2.6 volt. So we can go ahead and say, okay, we have 12 volt power supply. We have 1.7 volt, which we subtract from this voltage budget. We have 2 volts plus minus 1 volt swing, minus 2 volt. And then we don't want to get into the clamp region here. The 2.6 we're going to reduce and then divide it by 10 milliamps, so we have 570 ohm here. Then I simulated this whole circuit in LTSpice. First made the DC point operating point simulation to check if the theory and what we measured is really equal. And then of course I made a transfer simulation to see how if you see any distortion or any clamping of the output. And so LTSpice is a rather old program, but still maintained and still widely used. It's simple and it's accurate, and you can have all kind of different SPICE simulation software out there, but in the end it's all PSpice, and they all use the same models and you always get the same results. It's just you like the user interface, you don't. I'm not so fan of this LTSpice user interface, but it's okay. And then of course one important characteristics of this amplifier stage here is the output load, the output impedance of this amplifier. And you know, maybe to measure an output impedance, what you can do is you put a load at the output and change the load such that the output voltage from no load to your given load is 50%, because then you have a voltage divider from the output impedance and the load impedance. And if this voltage is then at 50%, the load voltage is equal to the output impedance. And in our case, it's roughly around 700 ohms. And these JFETs are well known that they have a rather high output impedance. And this is not very, very nice in my case, because this amplifier, this 8603, is expecting about a 100 ohm. It has a 100 ohm input impedance, and you should match these impedances. And if you have a voltage source with 700 ohm output impedance, it's going to be too much loaded by amplifier, and therefore I use a 2N3904 common collector circuit emitter follower to reduce the rather high impedance from the first stage to a low impedance to feed the input of the last amplifier here. So now let's calculate this common collector. Here again you have to choose a desired collector current. I did pick 3 milliamps and allow enough swing here at this transistor, this resistor of, let's say, 3 volt. I want to have at least 3 volts here. So we have 3 volts plus 0.7 volt at this point, and then with this 3.7 volts here, you can, and you pick maybe a 10K resistor down here. This R3 has to be 22K. And of course, you make another simulation. This is what we calculated, 3 volt and 3.7. We simulated 2.96 and 3.64, so that's fine. That's just perfect. And we're gonna check on that on the bench again, then in real world, if that's exactly, or if that's what we see then in our circuit on the bench as well. But however, I didn't like it, my first idea to have 3 volts at this point. I think it's usually good practice if you keep this point somewhere in between 12 volts and 0. So somewhere in the middle. So you always have more or less the maximum possible output swing. And therefore I changed the R4 from 10K to 22K. Move this point all up to roughly around 6 volts. And have it more centered at the output. Doesn't really matter because in our case we have such small input signals anyway, but it's good practice. And now, of course, I did the same thing with the output impedance here. I was looking for what's approximately the load. R6 is the load. With how much resistance can be loaded, the output, that the output voltage drops by 50%, and that's at around 20 ohms. So we have a very nice output impedance, low enough to feed without any problems this next amplification stage. So let's take a look at what we see on the bench. We are looking at this amplifier I did build up here on this PC board. Let me see if I can zoom in a little here. You see here on the left side, this is the input, that's the output. The input signal is decoupled with this 100 nanofarad capacitor and is then applied to the gate of the JFET, that's the J310. You have the drain and the source. The gate is pulled down with a 1 mega ohm resistor, and since the gate has no input current, this is virtually pulling down the gate to ground. On the other hand, you have on the source a resistor. It is, we calculated 160, 170 ohm. So that's this transistor here. And you have a transistor on the drain of 560 ohm, roughly. 560, 570. I had to take what I have here in my lab. And then the output again is decoupled to the base of the 2N3904. The 3904 has a voltage divider on the base with 2 times 22K. And then we have a 0 resistor all the way up to the from VDD, from the power supply to the collector. This is a common collector circuit, or emitter follower, as you say as well. And the emitter is, the current on the collector emitter is limited by a 1K resistor. And the output again is decoupled with this 100 nanofarad. So what I want to do now is I simulated the DC operating points. So how this whole circuit, this whole amplifier is biased, and we want to measure that, if we can see if the real life somehow matches the simulation. You see here the amplifier again, and these are the main DC points I want to check on. That's this point here on the drain. It should be around 6 volts. And this point here at the source should be about 1.7 volt, something around that. And then we have this point, this voltage divider should be roughly between 0 and 12 volts, so 5.7 we have simulated, and the output is also in between, or at least almost in between 12 and 0. So we should have enough swing on the output, but of course with these low voltage inputs and these low antenna signals, swing is not really a problem. But it should be around 5 volts. So let's see if we can measure this. First we measure the power supply, that's 12 volt, that's fine. Then we measure this point here, the drain voltage. That's here. It is 5.9 on LTSpice, and here it is around 6.3. I think that's okay. I mean, the resistors are not equally exactly as we calculated, and of course the JFET itself has some tolerances, so that's a fine. That's within all the possible tolerances. And then the voltage on the source here should be 1.7. It is 1.6. That's fine too. And then we have the voltage divider. The voltage divider at the base should be 5.7, and it is 5.7. That's spot on. All right, and the last point is here at the emitter. It should be 5 volts, and it is 5 volts. Perfect. So that's fine. So we verified simulation and real life matches pretty well. So I'm happy with that. Let's take a look at the simulation results. First, we want to look at the transient simulation of this whole amplifier. We have an input frequency of 3.5 megahertz at 0.1 peak voltage at the input. And you see the green curve is the input. It's plus and minus 100 millivolt. So it's 200 millivolt peak. And the output is roughly about 410 millivolt peak. And if we change these frequencies from 3.5 to, let's say, 7 megahertz, we have the same amplification. It's still at about 410 millivolt the output, and the input we didn't change. And even at 14 megahertz, we won't see any difference. So we will see then later on the bench that on the bench in reality this is totally different. What we can do here too is quickly change to an AC analysis. we want to start at 1 megahertz and stop at 20 megahertz. Okay, let's go. Let's get rid of the phase. We only want to look at the amplitude. You still have your input at 0.1 volt peak, and you have the output, and that's about, let's say that's minus 20 dB, that's minus 13 dB. You have something like 7 dB, 6-7 dB amplification from input to output at 14 megahertz. No, sorry, at from 1 megahertz to 20 megahertz. And you see it drop a little bit. You maybe lose a dB or half a dB at the higher frequencies. That's absolutely expected. But in reality, we see a much wider difference. This is very, very ideal. I mean, you never have a circuit like that in real life. I mean, you have capacities and inductances all over the place. And since this is such a high impedance input and such a high impedance output, this is very sensitive to all kind of stray capacities and stray inductances. So we will see then on the bench, reality is totally different than what we see here on the simulation. So we want to measure now the AC transfer function of this amplifier. You see the amplifier back here, as we already know it. And this is my Zigbee, and we have set it up to 3.5 megahertz, and you can see on the scope we have a 200 millivolt peak a signal here, and so it's a 10 to 1. The probes are set to 10 to 1, not 1 to 1. So I'm not loading the small signals and the high frequencies too much. So we have a 200 millivolts peak on the input, and we have on the output a roughly 670 from cursor 1 to cursor 2, 670 millivolt peak. That's at 3.5 megahertz. Now let's change frequency to 7 megahertz. 7. So we're all set here. 7 megahertz, still at 200, a little bit too much. I'm not so happy with this Zigbee really. It doesn't hold the output voltage over frequency very well. But it's roughly again 200 millivolts on the input, peak to peak. And on the output at 7 megahertz, we get, let me see, let's adjust the cursors. The top peak, the bottom peak, and we get about 964 millivolts. Okay, and then we're going to change the frequency to 14 megahertz, and you see, interestingly, the amplification increases here. We have now 9 megahertz, 10, 11, and it drops again, 12, 30, and it drops really badly. And at 14 megahertz, we have a poor amplification. Let me see. So now here we go. And what we have is peak to peak, we get about 390 millivolts peak. Oh, however, I have to adjust the amplitude again. I didn't see that. It dropped to 170. So increase it up to 200 millivolts peak. So now we have 200 millivolts peak here, and I have to measure again the peak voltage. So what we have is 463. So it's roughly a multiplication by time by 2 at 14 megahertz. So let's quickly look at another simulation. We saw on the bench that at low frequencies this amplifier has a rather low amplification. Then the amplification increases with frequency and has a peak at roughly somewhere between 5, 7, 8 megahertz, and then drastically drops at roughly around 12, 13 megahertz. And you wonder, where does that come from? Since the simulation before was so wonderfully just flat over frequency. And this has something to do with all possible stray capacities and maybe even inductances. I quickly made a simulation and I simulated a coupling capacity between the drain and the source of 30 picofarad, and maybe even a coupling capacity from source to ground. And I did pick here 300 picofarad, which is very high, but I wanted to show you this effect here. And of course you have couplings here and there also from the gate to the source and to the drain. It's not so easy to really understand how much is where and how does this all affect the circuit. But understanding that these stray capacities, they have something to do with the package of the component. It has something to do with the circuit board, the distance of the traces, what kind of traces do you have, and so on and so on. But you can see here in the simulation with these figures that it is rather realistic that these different stray capacities can affect your amplification significantly. And well, that's what we've seen and that's what we have, and we have to more or less live with it and optimize the circuit and optimize the circuit board in a way that you get rid of all those as good as possible.